Hello everyone. Now we will discuss the next topic of Cmos, that is the voltage transfer characteristic of Cmos inverter. This is the voltage transfer characteristic of a Cmos inverter, and this is the circuit diagram of the inverter. Here we will see the variation of output voltage of the inverter with respect to variation in the input voltage. That is nothing but transfer characteristic. We will be, if you recall the operation of CMOS inverter, we discussed that we have only two voltage levels in our digital circuit. This is a digital circuit which is nothing but CMOS inverter, where we will be having only two voltage levels, 0 and 1. 0 here is ground and 1 means the voltage VDD. Fine. So what we do in practical conditions, we don't have very fixed voltage at input level. There may be small variations in input voltage. Reason being, there may be certain noises which are superimposed on the input signal, and there can be a range of input voltage rather than the fixed voltage of 0 and plus VDD. We will see that variation. So here what we are assuming is the input voltage is varying from 0 to VDD. When we vary the input voltage from 0 to VDD, we will see the corresponding variation in output voltage of the circuit. We will be dividing the range of input voltage into different segments. The first segment is 0 to threshold voltage. Second segment will be threshold to half of the supply voltage. Third segment, half of the supply voltage to VDD minus VT, and fourth segment will be VDD minus VT to VDD. But there is a set of assumptions here. Set of assumptions is both PMOS and NMOS of the inverter are symmetrical and identical. This is what we assume. Both are basically assumed to be matched transistors. Rather than saying symmetrical or identical, we will say these are matched transistors. So set of assumptions is let the threshold voltage of NMOS is same as the threshold voltage of PMOS, and that is equal to VT, which is denoted by VT here. VT stands for threshold voltage, VTN stands for threshold voltage of NMOS, and VTP stands for threshold voltage of PMOS. That is one assumption we will be carrying out throughout this particular topic. Second is, we assume that the transconductance parameter is same for both the transistors. That is nothing but mu n C naught x into W n by Ln is same as mu p, I will be using subscript small, and mu p C naught x into Wp by Lp. Fine. This is what is the assumption is. Fine. So here, if this is same, this will be getting cancelled out, assuming the same capacitance for this. So mu n Wn by Ln is equal to mu p Wp by Lp. This is what we have. Fine. Here, if you take same length of the channel, what I mean to say is, if length of channel in NMOS is same as length of channel in PMOS, so let Ln is equal to Lp and that is equal to L. That is again assumption. So you will have mu n Wn equal to mu p Wp. But remember, mu n by mu p is equal to Wp by Wn. But if you remember the semiconductor theory, the mobility of electrons is 2 to 3 times the mobility of holes. Mobility of electrons is 2 to 3 times mobility of holes. If it is 2 to 3 times, so that means this implies the width of the channel will of p type PMOS, we can say it is 2 to 3 times the width of the channel in NMOS. That is what you have. Fine. So if both the transistors are matched, that means their threshold voltage is equal, their length of the channels is equal. In that case, the relationship between width of the channels will be this. This is one assumption we will be carrying throughout this topic. Now, let us see the next part of the topic, that is the different segments of the input character, that is voltage transfer characteristic. Fine. Let us see the first one. I am repeating, I have divided this complete range of input from 0 to VDD into different segments. Region we will see one by one. So first case is when input voltage is less than the threshold voltage. But before we go to that particular range of input voltage, we have the two transistors. In operation of the circuit, we have seen here the transistors are operated in either in cutoff region or in ohmic region. That means when device is in cutoff, that is just like an open switch. When device is in ohmic region, that behaves like a closed switch but offering some finite resistance, right? So MOSFET is always a resistive type of switch. It is not an ideal switch. It offers some finite resistance when it is behaving like a closed switch. Fine. So now let us see the behavior of NMOS. In case of NMOS, we will be talking about two cases. Case 1 when it is in ohmic region, case 2 when it is in saturation region. Why in saturation? Why not in ohmic? Why in saturation? Why not in ohmic? The NMOS transistors will be working in cutoff and ohmic, but remember, when it changes its state from ohmic to cutoff, it always passes through the saturation region of operation. If you remember the characteristic of a MOSFET, this is cutoff, this is ohmic, and in between there is a saturation region. So whenever operation shifts from cutoff to ohmic, it passes through this region, which is nothing but saturation region of operation. So you cannot ignore the operation in saturation region, even though we are talking about the operation of MOSFET in ohmic and cutoff, but you need to discuss saturation region of operation as well. Fine. So when we talk about NMOS, so we will see its operation in both ohmic and saturation region of operation. Fine. Similarly, PMOS will be again, although it is operated in cutoff and ohmic region for this case, that is switching operation, but it will always pass through the saturation region of operation when its it changes its state from ohmic to cutoff or cutoff to ohmic region. Fine. So, let us see the expression of drain current. The drain current is of course same for both the transistors ID. Fine. Now, the drain current for NMOS, let us talk about ohmic region. For ohmic region of operation, the drain current of NMOS is given by, or I will say IDN for NMOS, although it is same for both the cases, for both the transistors. IDN is equal to mu n C naught x by 2 into Wn by Ln into the gate to source voltage of what? NMOS minus the threshold voltage whole square. But there is a condition for operation in I am sorry, this is for saturation region. So, what will be there for ohmic region? That will be VGSN, that is VGSN minus threshold voltage multiplied by VDS minus 1 by 2 VDS whole square, and this 2 will not be there in case of which region? For ohmic region of operation. Fine. And condition for operation in ohmic region is what? The drain to source voltage of NMOS must be less than or equal to VGSN minus threshold voltage. That is the condition for operation in ohmic region. But if you see from this part here, what is VGSP? What is VGSN first? VGSN is equal to VI. You can please see with this is VGSN not P. So VGSN is equal to VI. Second part, what is VDSN? VDSN is equal to V naught. Fine. So if you put VGSN equal to VI here, we put VDSN is equal to V naught here. So what do you get? The drain current for ohmic region for NMOS is mu n C naught x Wn by Ln into Vi minus threshold voltage into V naught minus 1 by 2 V naught square. And what will be the condition? V naught less than or equal to Vi minus threshold voltage. So what I have done? I have obtained drain current of this NMOS transistor for ohmic region of operation in terms of output and input voltages like this. Fine. Although you don't have direct questions on these formulas, but this is important for MOSFET circuits. Fine. So you should remember this formula. This is important from examination point of view. There can be numerical based on this expression. Fine. Similarly, let us talk about the saturation region. Saturation region for what? For NMOS. We are first of all talking about the behavior of NMOS. Expression of the drain current for NMOS in ohmic and saturation region in terms of output voltage and input voltage. Fine. But before I proceed for the ohmic region, I will give you one more expression. Remember, in case of ohmic region of operation, there is one important parameter of NMOS. What is that parameter? In ohmic region, MOSFET offers a finite resistance, and that resistance is what? That resistance is given by, that is RDN or RDSN, whatever, that is drain to source resistance of NMOS. RDSN for this is nothing but 1 by mu n C naught x into Wn Ln into VGSN minus threshold voltage. And you know what is VGSN? That is this relation. So this is equal to 1 by mu n C naught x into Wn by Ln into VGSN is what? Vi minus threshold voltage. So I get the drain to source resistance of NMOS when it operates in ohmic region, and that in terms of what? Input voltage. Fine. This is important from examination point of view. This is important from examination point of view. You should remember these formulas. Fine. Although I am just writing the expression of the drain resistance of a MOSFET, but in terms of input and output voltage, in terms of input voltage here you can say. Fine. Now, let us see the saturation region. In case of saturation region of operation, the drain current is having different expression. What is that expression? Let us see the expression. I am talking about NMOS only. Fine. So, in case of NMOS, the expression of drain current ID can be written like this. The drain that is for saturation region. For saturation region of operation, the drain current of NMOS is given by mu n C naught x by 2 Wn by Ln into VGSN minus threshold voltage whole square. Fine. What is the range? Range or condition, you can say condition is VDSN should be greater than or equal to VGSN minus threshold voltage. You should remember these expressions. These should be on your fingertips. These are very important from examination point of view, especially in MOSFETs. Fine. And there are a lot of questions in CMOS based on these formulas. Fine. Now, again, what is VGSN? I have just given you the expression, that is Vi. What is VDSN? I have just given you the expression, that is V0. So what I get? The drain to source current is equal to mu n C naught x by 2 Wn by Ln into Vi minus threshold voltage whole square. Condition is what? VDSN is V0. So V0 greater than equal to Vi minus threshold voltage minus Vt. That's what you have. Fine. This is the condition, or this is the expression of drain current in terms of input and output voltage, and that is the condition for operation in saturation region. These are the conditions for NMOS. Now we will see the conditions for PMOS. Now I will be going in reverse way region because I have already written, so there won't be need of repeatability. You know, for saturation region, the current of PMOS is what? Expression is similar. The only thing is put subscript P here, subscript P here, subscript P here, subscript P here. But remember, VGS is negative for PMOS. So instead of writing VGSP, I will say SGP. You should for PMOS expression here, it should not be VGS, it should be SGP, and put mode here. That is the difference in expression of drain current for PMOS. It should be the threshold voltage of PMOS is negative. So put mode here, and instead of VGS write VSG, so that is a positive voltage. So, and similarly here, instead of VDS it is SDP, because that will be a positive voltage. Similarly here, VSGP, put mode here. That's it. So that is how we get the expression. But here VSGP, please see the source to gate voltage for PMOS, that is VDD minus VI. So the expression of voltages here will be different. VSGP is nothing but VDD minus VI. Similarly, VSDP, that is equal to what? VSDP is VDD minus V0. So VDD minus V0. And if you put these expressions here, you will get the expression of the drain current for saturation region of PMOS in terms of input and output voltages. Fine. So let us see the expression. That is mu P C naught X by 2 into WP by LP into VSGP is this VDD minus VI minus threshold voltage mode whole square, and VSDP is what? VDD minus V0 greater than or equal to VDD minus VI minus mode of threshold voltage. That is the condition, and you can see VDD and VDD is cancelled out. That is the condition, and this is minus, so you can make it V0 less than or equal to VI, fine, plus VTT, mode of VT. This is the condition of operation in saturation region of PMOS, or that is the condition for PMOS. Fine. Now we can drive the relationship, similar relationship for ohmic region of operation. Fine. So now let us see the operation in ohmic region, or we can say the expression of drain current for ohmic region in terms of input and output voltages. So for ohmic region, the expression we have seen, or we can write the expression just like NMOS. The expression of drain current in ohmic region for PMOS is given by, what is the expression? That is IDP is nothing but mu P C naught X by, or not 2, that is into WP by LP into VD, that is V SGP minus threshold voltage mode of it into VSDP minus 1 by 2 VSDP whole square. That is the expression. Condition is VSDP should be less than or equal to VSGP minus threshold voltage mode of it. That is the condition for ohmic region of operation. Fine. And we have just seen, we can rewrite that expression again. So IDP is equal to mu P C naught X by 2 WP by LP into VSGP is what? VDD minus VI. So VDD minus VI minus threshold voltage mode into VSDP is what? VSDP is VDD minus V0. So VDD minus V0 minus VDD minus V0 whole square by 2. Condition here becomes VDD minus V0 less than equal to VDD minus VI minus VT threshold voltage, or this gives minus V0 less than equal to minus VI minus VT. That's it. Fine. So, or this gives V naught greater than, if you remove negative sign, it will be greater Vi plus V threshold. That is how we drive the condition for ohmic region, and we find the drain current in terms of output and input voltages. Fine. So, now we will see the different cases one by one. That condition will be range of input voltage and operation of the different, you can say PMOS and NMOS. Let us see the range of input voltage. Here I will be again taking the different segments of input voltage. Let us see that. First we will be taking case 1. Case 1 is what here? Case 1 is input voltage is less than or equal to the threshold voltage. That is your first case. Fine. So, case 1. Case 1, input voltage is less than threshold voltage but greater than 0. This range of input voltage. Now, let us see the operation of this. See your NMOS. For this, let us see NMOS. Behavior of NMOS. I will write the expression of VGSN. What is VGSN for NMOS? VGSN for NMOS is Vi, right? And VDSN is nothing but V naught. Similarly, VSGP is nothing but VD minus Vi, and VSDP is what? That is VDD minus V naught. These are the expressions of the voltages of the NMOS and PMOS, right? So, for PMOS, this is the expression. Fine. Now, PMOS, NMOS, let us talk about NMOS first. Here, Vi is same as VGSN. So, for above range of input voltage. For this range of input voltage, what will be the range of VGSN? Why I am talking about VGSN and VDSN? Because the range of the gate to source voltage and drain to source voltage will be deciding the operation of the region of operation of the MOSFET. So, here we know Vi is what? VGSN. So, for this range of input voltage, what will be the range of VGSN? So, VGSN will be in this range. Why? Because if input is in this range, so VGSN is same as input. So, this is the range of VGSN. And remember, if gate to source voltage is less than threshold voltage, that means your MOSFET is in cutoff region. So, here NMOS operates in what? That is, it operates in cutoff region, right? So, that means for this range of input, your NMOS, or we can say QN, is in cutoff. QN must be in cutoff region, right? That's what you have. Now, for this range of input voltage, when input is less than threshold, you can split see if Vi, from here what do we get? Vi is equal to VDD minus VSGP, right? This is what you have. Similarly, what is V naught? V naught is VDD minus VSDP. That's what you have. Fine. So, here important point is when input voltage is between this range, so if you talk about NMOS, this is what you have. For PMOS, let us see the range. If input voltage is in this range, so this must be in this range. So that means VDD minus VSGP is less than the threshold voltage. Fine. So that's what you have. Fine. So now if you have this range of the input voltage, that is nothing but Vi is this, so I put this here, so you will get range of what? Range of the gate to threshold, the gate source to gate voltage. Let us see how to modify it. So VDD minus VSGP is less than threshold voltage, we can say, or you can take this here, VDD is less than threshold voltage plus VSGP, right? Or we can say VSGP is greater than VDD minus threshold voltage. So VSGP is quite large, VDD minus VT. Fine. This is quite large. So it means this device is, this voltage is definitely more than the threshold voltage. Why? Because we consider this voltage is very large as compared to threshold voltage. Supply voltage is very large as compared to threshold voltage of the device. If source to gate voltage is much larger than the threshold voltage, so device must be on. And what do you mean by on? Either in ohmic region of operation or in saturation region of operation. Fine. But we have already seen that the PMOS and NMOS, both transistors work in ohmic region of operation for inverter operation. Fine. So if it is on, it must be working in ohmic region, but there is always possibility that it may be working in saturation region as well. So let us see how to find whether it is working in saturation region or ohmic region of operation. This is sure, this condition gives you one thing. It tells you one thing. What? It tells that it is not working in cutoff. So for this range of input voltage, Q1 is in cutoff and QP is either in saturation or in ohmic region of operation. So now let us see the voltage VSDP for this range of input voltage, right? So VSDP is equal to what? VDD minus V0, right? Fine. So here when it is on, if it is on, initially when this voltage is less than threshold voltage, when this voltage VGSP, initially Vi is between this range of 0 to Vt, this is definitely operating in that is cutoff region. So this voltage is large and this is driven directly to the saturation region of directly to the ohmic region of operation. For this range of if you see the expression, that is VSDP is equal to VDD minus V0. Now V0 will be for input voltage between 0 and threshold voltage, right? Your V0 is approximately equal to VDD. Fine. And that condition we have already seen for ohmic region of operation. For ohmic region of operation of the PMOS, that is VSDP is equal to, that is VSDP is VDD minus V naught. And if you recall, I have given you the expression for PMOS for ohmic and saturation region. For ohmic region of operation, what is there? For ohmic region of operation of PMOS, VSDP should be greater than VGSP minus threshold voltage, less than, not greater. For ohmic region of this, for ohmic region of PMOS, for ohmic region of operation of PMOS, your relation between VSGP and VSDP is this. Fine. But what is VSDP? That is V naught, VDD minus V naught. And what is SGP? That is VDD minus VI. Fine. It is mode, so minus VT. So this gives V naught minus less than equal to VI minus VT mode, or this gives V naught greater than equal to VI plus V threshold. Fine, mode of it. This is what you have. Fine. Now, interesting point here is, for this range of input voltage, output voltage is this. It means it is more than twice the threshold voltage. Fine. So, if it is the range of output voltage, that means this voltage is, in that case, this voltage is high. More than twice the threshold voltage means for this range of input voltage, your output voltage must be high. On upper side, we can say. Now, I repeat the point again. If you see VSDP is VDD minus V naught, and V naught here is more than twice the threshold voltage. So that means VSDP will be smaller. Fine. Because you are subtracting twice the threshold voltage from the VDD. So, and when VSDP is small, if you remember the characteristic of the circuit, this is drain current, this is VSDP, and this is the characteristic. Fine. So, when VSDP is small, the region of operation will be nothing but ohmic region. I am just giving you the idea, but don't go into this mathematical analysis for handling the questions in exam. You must remember this characteristic directly. So, here QP is in what? That is in ohmic region. Fine. And if input voltage is between VT and VDD by 2, VTT and VDD by 2, your operation of QN will change. How? Let us see that. Let us see the case 2. In case of case 2, input voltage is between threshold voltage and that is threshold voltage and VDD by 2. This range of input voltage from here to here. For this range of input voltage, what will happen? Your gate to source voltage for NMOS will be definitely more than threshold voltage. So this will be turned on. And what do you mean by turned on? Turning on means your device will change its operation from the cutoff region. And remember, this is the cutoff region for MOSFET. So when it changes its operation from cutoff region, it passes through what? Saturation region. It will never shift its operation from cutoff to ohmic directly. It will be definitely going through saturation region. So when input voltage becomes more than threshold voltage but less than VDD by 2, your NMOS will be working in saturation. So what I mean to say is, for this range of input voltage, Qn is in saturation region. Fine. And what will be your PMOS? In this case, this is Vt, this is VDD by 2. Why? Because this is your input voltage VDD minus VIGP. So input voltage is between this range, and here again if you drive the relationship for a relationship between output and input voltage, in this case as well, initially it was on, this voltage was very high when VSGP was very high, and this was small, it was in ohmic region. So for this range of input voltage as well, this is where your QP is again in ohmic region, but your Qn enters into what? Saturation region. I repeat, initially Qn is in cutoff region, QP is in ohmic region. Again, when threshold voltage become more than, your input voltage becomes more than threshold voltage, your Qn enters into saturation, QP remains in ohmic. So it means for this range from here to here, QP is in ohmic region. Fine. And remember, if both transistors are matched transistors, Vi is equal to VDD by 2. I repeat, if both transistors are matched transistors, in that case your voltage transfer characteristic is symmetrical about this vertical line, that is Vi is equal to VDD by 2. When Vi is VDD by 2, so your gate to source voltage for NMOS will be less than, or we can say this is VDD by 2, and VSGP will be again, that is VDD by 2. Why so? VSGP is what? VDD minus Vi. Vi is VDD by 2, so VSGP will be VDD by 2. If this gate to source voltage is same for both the transistors, so here both will be operating in saturation region. Remember, which transistor? Both QP and Qn. So QP and Qn will be operating in saturation region when input voltage is VDD by 2. Fine. Now if you switch over from here to here, condition will be similar, but here it was in saturation, here Qn will be in saturation. Then VDD minus Vt is similar to this part, Vt to VDD by 2. So from here to here, QP will be in saturation, and from here to here, Qn was in cutoff, so QP will be in cutoff. So remember this. Fine. In nutshell, rather than entering into the mathematical analysis, I will summarize whatever we have discussed, and this is what you need to remember. Fine. What? Case 1. Case 1 is what? Input voltage is less than 0 and threshold voltage. When input voltage is between 0 and threshold voltage, Qn is cutoff, that is in cutoff, QP is in ohmic. That is summary. Case 2. Vi greater than threshold, less than VDD by 2. Your Qn will enter into saturation region, but QP will be in ohmic region. Right? Then case 3. Your input voltage becomes more equal to VDD by 2. When input voltage is VDD by 2, Qn is in saturation region and QP is also in saturation, both enter into saturation region, right? Then case 4. Case 4 is what? Vi greater than VDD by 2 but less than equal to VDD minus V threshold. Fine. For this range of input voltage, what has happened? This ohmic, it has switched from ohmic to saturation. Remember, whenever device changes its state, it will always go through the saturation. If it is a ohmic, it will go into saturation then to cutoff. If it is in cutoff, it will go into saturation then into ohmic. That's how it goes. Fine. So for this, QP was, you can see from here, Q1 was in cutoff, it has entered into saturation. So here Q1 will be entering into ohmic region, right? And QP will be entering into, please see, it was, QP was ohmic, saturation, right? So it will remain into region here, saturation. And case 4, why it is? Because it is symmetrical. So input voltage greater than VDD minus V threshold and less than VDD. So this will be giving me QP into cutoff and Q1 into ohmic region. That is, Q1 enters into this. Q1 was here saturation. I'm sorry, I'll just rectify. When it was in saturation here, Q1 is in saturation, so here from here to here Q1 will be in ohmic region, right? So Q1 is in ohmic region. Now again see the characteristics from here. From these characteristics, what we find? 0 to threshold, Q1 is in cutoff, QP is in ohmic. Start from here. QP is in cutoff, Q1 is in ohmic. Come here. Qn enters into saturation, QP is in ohmic. Come here. Qn is in ohmic but QP enters into saturation region. Come here. Both are in saturation. So because of symmetry, you will be able to remember the operations. Why it is important? Because sometimes you are given the input voltage, value of the input voltage, and you may have to find the current, drain current of the NMOS or PMOS, and expression of drain current depends upon the region of operation of the device. So accordingly, expression of the current will change. So from that point of view, you should remember the range of input voltage and corresponding operation of the MOSFETs. That is the only point you need to remember. You should remember the shape of the characteristic, number 1. Number 2, you should remember the regions of operation of MOSFETs. But there are two important voltages here. Remember, there is one point where if you draw the slope, that slope is -1, and that voltage, input voltage on the characteristic is nothing but which is known as VIL. This VIL, I am repeating, you draw the slope of -1 at this part of the characteristic. That value of input voltage is VIL. VIL is the highest input voltage for logic 0. From here to here, from this range to this range, this is range of input voltage for which logic? For logic 0. Fine. Similarly, if you see the range of input voltage, you draw the characteristic, draw the slope here of slope minus, draw a line of slope -1 here. From here to here, this range, this is VIH. Remember, that is the lowest level of input voltage for logic 1. So from here to here, it is logic 1. So what is VIL? VIL is the highest level of input voltage for logic 0. VIH is the lowest level of input voltage for logic 1. Fine. Now, we will see the relevance of these two voltages. This is important. VIL minus 0, and remember output voltage has got only two levels, which are this is V that is VOL is 0. The output voltage for logic 0 is 0, and output voltage for logic 1 is VDD. Fine. So in nutshell, from the voltage transfer characteristic of CMOS, we have got the range of input and output voltages. Fine. That is, what is the range of input voltage? Range of input voltage and output voltages. So highest level of input voltage for logic 0 is VIL. I repeat, highest level of input voltage for logic 0, or we can say range of input voltage for logic 0, that is VI greater than 0 less than VIL. Now range of input voltage for logic 1, that is VI should be greater than VIH and less than VDD. Fine. Now output voltage for logic 0, that is V output is equal to 0. Then output voltage for logic 1, that is V naught is equal to plus VDD. That's it. So it means we have got the range of output voltage for logic 0 and logic 1, but we have got the fixed voltages at output for logic 0 and logic 1. So this is the transfer characteristic, voltage transfer characteristic of the CMOS. In next topic, in next video, we will see the noise margins of CMOS circuits. So just wait for my next video. Thank you very much for watching the video.